Our discussion today plunges right into one of the deepest, philosophical conflicts in modern science, the meaning of quantum mechanics itself. Down at the subatomic level, particles, they just defy classical physics, behaving in ways that really challenge our fundamental notions of space and objective reality.
And that strangeness is precisely the core issue, isn't it? Quantum mechanics is, it's indisputably the most successful and predictive physical theory we have, ever. Yet it forces us into these conceptual corners that, frankly, even its founders found deeply troubling. The mathematics works perfectly, but the story it tells about, the physical universe, it just feels kind of broken.
Right, so today we're focusing on the central interpretation that's used, pretty much universally by practicing physicists and engineers, the Copenhagen interpretation, or CI. If the math is so successful, as you say, surely we have to accept the operational description it provides. So the central question before us today is this: does the Copenhagen interpretation, which holds that a quantum entity exists simultaneously in a superposition of multiple potential states until the act of measurement causes a state determination, offer a fundamentally complete and satisfactory description of physical reality?
I'm afraid I just don't buy that it's complete. My position is that the CI provides a brilliant recipe for prediction, yes, but it's conceptually incomplete, and it's prone to paradoxes, limitations that were famously voiced by giants like, Einstein and Schrödinger.
Okay. Well, my position is that the CI isn't just a theory, it's really the proven operational reality of how nature behaves at the fundamental level. Its description is overwhelmingly supported by the empirical evidence we gather when we, force nature to reveal its mechanisms.
Then let us see where that evidence truly leads us.
Okay, so the foundation of my perspective rests really entirely on observation. The CI provides the only truly effective model for interpreting the famous double-slit experiment, particularly when it's conducted with individual particles like photons or electrons. You recall the setup. When a single photon is fired through the slits, and critically, we use no detector to track its path, it somehow generates an interference pattern on the screen behind it. Now, this demonstrates that the photon acts as a wave of possibilities, basically traversing both slits simultaneously.
Okay, I grant the phenomenon entirely. The interference pattern is real. Absolutely. And the wave of possibilities is, a necessary mathematical construct to predict the eventual outcome. The paradox, however, lies in how the CI interprets the reality of that wave before the measurement.
But the key observation is the state determination, what people often call the collapse. The moment the very instant a sensor is put in place to record which slit the particle passes through, that interference pattern just vanishes, gone. The particle instantly stops acting like a wave and reverts to behaving like a localized corpuscle, hitting the screen in only two defined spots right behind the slits. This reality, this potential instantaneously crystallizing into a single outcome upon interaction with a measuring device, is precisely what the CI claims. And look, this framework isn't optional. It's the backbone of modern quantum technology. Think of quantum computers. They rely entirely on qubits existing in a superposition of 0 and 1 simultaneously. The theory works, and its working, I argue, validates its description of the underlying mechanism.
That's a powerful argument focusing on the empirical effectiveness, I agree. But we have to ask, at what conceptual cost? The CI, I think, fails philosophically because it insists reality is merely potential, this probability cloud, until it's forced into existence by measurement. And this leads to truly absurd conclusions regarding objective reality that just defy any kind of common sense.
Well, common sense based on the scale of bowling balls and planets, perhaps. Not necessarily the quantum realm.
No, based on rigorous philosophical critique. Consider the specific objection offered by Einstein, encapsulated in his famous statement that the creator of the universe does not play dice. Einstein was, I think, right to demand objectivity. That is the bedrock of classical science. He found the whole idea that the universe should be governed solely by statistical probability, that essential properties like location, momentum, spin, are fundamentally undefined until measured, to be profoundly unsatisfactory. He even mocked the idea that objective reality depends on the observer, famously wondering whether the moon's existence ceases to be objective if we all just happen to turn away.
That is persuasive rhetoric, certainly, but it focuses heavily on our classical intuitions.
not the hard experimental results.
Okay, but what about Schrödinger's cat? That thought experiment wasn't just idle musings. It was devised specifically to ridicule the CI by demonstrating that if we logically apply the concept of superposition to the macroscopic world, we reach an absurdity. If a radioactive atom is truly in a state of being simultaneously decayed and not decayed, then the linked cat, following the CI logic, must be simultaneously alive and not alive. This conceptual absurdity, I believe, demonstrates that the CI is incomplete. It just can't be the whole story if it leads to such logical breakdowns when you try to scale it up.
I absolutely acknowledge the philosophical weight of these historical critiques, but the cat paradox forces us to transition directly into our first central contention here, the role of observation in defining reality, and crucially, the physical mechanism that actually prevents macro superposition.
Exactly. If the CI is complete, it must explain why we only seem to observe superposition in the micro world. If, as the CI suggests, the photon is truly, existing in all those possible paths until we observe it, this fundamentally challenges our understanding of objective existence and location itself. How can something like location be merely a probability distribution rather than a defined singular state?
Because the experimental results compel this conclusion. We're not just asserting this out of thin air. The single photon experiment shows that the particle is acting as if it's in multiple states simultaneously. That wave of possibilities is, in some sense, real. And it only selects one location the very moment it interacts with a detector or some measuring device. This behavior is the reality revealed by nature. We simply must describe the universe as it behaves, however strange.
But does the experiment truly force this specific interpretation, or does the CI simply offer the most mathematically convenient way to model the data, leaving open other ontological possibilities? Things like hidden variables or perhaps even other realities?
And you still haven't quite resolved the cat paradox. Why don't we see everyday objects in superposition? Okay, fair point. And that brings us directly to a necessary refinement, or perhaps clarification, within the CCI framework, the concept of decoherence. The reason the cat paradox is resolved and why the CCI doesn't just scale up indefinitely to the macro world is that superposition is fundamentally incredibly fragile. It's unstable when exposed to the vast complexity of the environment. Decoherence is the physical process where a quantum system interacts with its surroundings, literally anything, photons, air molecules, radiation, and it instantly loses its quantum coherence, its superposition. The cat, being a large, warm, breathing organism, is constantly interacting with trillions upon trillions of particles in its environment. This environment acts as a continuous, relentless measurement device, effectively instantaneously collapsing the wave function and preventing any sustained quantum state. So the CI, particularly when including decoherence, does account for this boundary between the quantum and classical worlds.
That's a critical addition, decoherence. Okay, it explains why the weird quantum effects disappear at our scale, but it doesn't fundamentally change the conceptual problem of when or how the collapse happens, does it? I mean, if the environment is now the measurer, we've just replaced the conscious scientific observer with, say, the surrounding air. We're still keeping the strange requirement that reality requires some kind of interaction to define itself, and this kind of non-local strangeness, well, it leads us right to our next point.
Indeed. Where are you going with this?
Well, if we accept that interaction determines state, we still have to grapple with that truly bizarre consequence that Einstein famously called spooky action at a distance, quantum entanglement. Which brings us neatly to contention number 2, the paradox of entanglement.
Ah, yes, entanglement. It's perhaps the most difficult feature of quantum reality to really wrap your head around. Yet it is utterly verifiable experimentally.
And it fundamentally undermines, I argue, the CI's attempt to define states purely through localized, independent measurement. Think about it. When two particles, like linked electrons, are created in an entangled state and then separated, maybe by vast distances, the measurement of one instantaneously determines the quantum state, let's say spin up or spin down, of the other one. Instantly.
regardless of the distance separating them.
It is a demonstrable physical phenomenon. Absolutely. Bell's theorem and all the subsequent experimental tests have verified this. This instantaneous correlation is faster than light, apparently, and it's a true feature of our universe. You measure electron A over here, find it spinning up, and electron B, potentially light years away, instantaneously registers a downspin. That's what happens.
But this challenges locality itself. If the electron only defines its spin upon a local measurement, right here, how can two electrons, separated by maybe astronomical distances, define their states simultaneously and in perfect opposition? It suggests some kind of relationship or informational link that exists outside the conventional space-time boundaries that the CI supposedly operates within. If the CI were truly complete, it should offer a satisfactory physical explanation for this non-local linkage, not just, well, a successful mathematical description of the resulting inverse probability. It describes what happens, but not how or why.
But that's precisely what the CI does do, in my view. It provides the most accurate mathematical description of this joint probability function. I'm not convinced that entanglement actually breaks the CI. Rather, the CI framework it accommodates this bizarre non-local reality as part of the interconnected nature of quantum states. It essentially proves that state determination, even if probabilistic, is non-local and instantaneous for entangled particles. We verified this reality countless times in labs, and the CI successfully models it. The fact that the universe operates in a non-local manner doesn't automatically mean the theory describing that operation is incomplete. Perhaps it just means the universe is stranger than our classical intuition allows for.
Perhaps. But that moves us directly to our final contention, I think. The critical distinction between practical effectiveness and genuine philosophical completeness.
Okay. And here, the predictive success of the theory absolutely validates its description of reality, in my opinion. We can move beyond historical thought experiments now to hard, current technology. Quantum mechanics and the concepts derived directly from superposition and probability waves allow for revolutionary technologies, most obviously the quantum computer. Take a Google Sycamore processor, for instance, a machine composed of only 53 qubits.
An impressive piece of engineering, undoubtedly, yes.
Well, this machine solved a highly complex calculation in just 200 seconds, a problem that it's estimated would have taken the fastest classical supercomputer at the time, IBM's Summit, something like 10,000 years to solve. This phenomenal power comes directly from harnessing superposition. Each qubit exists as both 0 and 1 simultaneously. So with 53 qubits, the system can explore 2 to the power of 53 possibilities. That's about 9 quadrillion potential computational paths all at once. This operational truth, the ability to physically represent and utilize that massive number of potential states simultaneously, means the physical mechanism described by the CIM must be real, in some sense, before those potential states collapse down into the single correct answer. The sheer utility validates the interpretation of the underlying mechanism.
Operational success validates the formula, the recipe, yes, but it does not, I insist, equate to fundamental truth about the underlying nature of reality itself. The fact that a quantum computer can calculate all those possibilities simultaneously, well, it merely highlights the very problem Einstein identified. What is the actual state of the system before the final, measured answer appears?
It is in superposition, defined by the evolving probability wave as described by the Schrödinger equation. The calculation is literally occurring across all those possible states simultaneously.
Exactly. The mathematics describes a highly effective formalism, a powerful map for predicting the outcome. But we still don't really know what the territory, the underlying reality, truly looks like beneath that mathematical surface. If the CI is complete, it must tell us the actual physical status of those 9 quadrillion states during the computation. Is the computer genuinely residing in 9 quadrillion parallel realities before the state determination, as, some competing interpretations like many worlds might suggest? Or is it just some abstract probability field? The CI gives us the effective formula. It works brilliantly. but it fails, I think, to give us a satisfactory ontological explanation for the physical existence of the system before that final collapse. The conceptual absurdities we talked about, the cat, the dice, they remain unresolved in terms of a satisfying narrative of objective reality.
But if the theory allows us to physically harness a state superposition to achieve computational feats that were literally impossible before, surely that practical control suggests we have correctly identified the mechanism. We are manipulating the simultaneous existence of possibilities. We should therefore accept the mechanism as described by the CII, at least until an equally successful, yet perhaps conceptually clearer, alternative mechanism is developed and, importantly, validated by technology.
I absolutely agree that the CI is the most effective descriptive tool we currently possess, and its predictive power is, well, unmatched. But I must maintain that its conceptual framework remains incomplete. It demands that reality be somehow undefined until observed, and it introduces these deeply counterintuitive non-local paradoxes like entanglement without fully explaining them. It gives us the how to build amazing technology, but it fails to give us a complete what regarding the nature of objective reality itself.
So ultimately, the Copenhagen interpretation, though definitely conceptually challenging, is the interpretation most powerfully supported by the sheer weight of evidence gathered from foundational experiments, like the double-slit, and functionally validated by the power and mechanism of quantum computers, where the state of superposition is harnessed practically every second these machines operate.
And yet, the conflict illustrates that even our most effective scientific